as I was listening to the keynote this morning, I was like, cool, you know, going to Mars, and then we're all going to travel there. And I thought, okay, what time zone are we going to use? And are we going to use base 12 time? And because the sun's going to be different, so a whole new headache, but it's not a problem we have to worry about just yet. But for us as software engineers, to truly understand the complexities of time, we really need to go all the way back to the ancient Babylonians and ancient Egyptians and really understand where they got this concept of time from. In 1500 BC, we knew that time had something to do with the sun, something to do with light, the Earth rotating around the sun, and the Earth rotating around its axis. So our ancestors quickly came up with the sundial. And the sundial had many problems. The sun would differ, the time would differ, the reading would differ, say, from here to Craigieburn. And what would be the exact time? And one of the things interesting about this one here, I don't know if anyone has managed to count, but how many of those little small triangles do we see? 12. This base 12 complexity isn't something that you can blame on us, software engineers and mathematicians. It's something that we've inherited. So this is one of the problems associated with it. The readings can differ with the clouds, and I mean like real clouds here, not like Google or AWS or something like that. So the readings differ. But we quickly found out that there's something interesting about this date, and that it's constant. And we quickly came up with water clocks. And it was the first time in human history where we found out that this was constant. And as soon as a water clock finishes dripping or a sand clock finishes dripping, we know that this was a certain amount of time. But there were problems associated with that as well. Now, if I was a servant in some aristocrat's house and I accidentally bumped the water clock, I would probably die, but different story. But the water clocks had their problems, evaporation, and things like that. But so far we've been speaking about the technology in the day. What about the technology or how we split up months? So our early ancestors knew that the Earth revolved around its axis and it was at an axial tilt, and the Earth rotated around the sun. Now they knew there was a longest day of the year and a shortest day of the year. So in about 46 BC, Julius Caesar, this person on the right, with consultation with various astronomers and scientists, decided to come up with, just like any good absolute monarch, a name, and he called it the Julian calendar. And this is the very same calendar that we use today, with the 12 months of the 12 Roman gods that we use today. But we noticed something interesting, that this longest day of the year was shifting year in and year out. Fast forward a few hundred years, in 1582, a few astronomers and scientists came together with this person on your left, Pope Gregory, and just like any good monarch, decided to come up with a correction to the calendar and name it after themselves. And I hope that if any of you here come up with a calendar that's more accurate, that you will name it after yourself. That real desire to want to tell the time didn't actually come intrinsically from time itself, but rather came from the problem of travel. You see, when we started traveling around the colonial era, we could tell latitude from the stars or the sky and whatever. But we couldn't really tell the longitude. And the way they would calculate the longitude is that there were two clocks. There was a clock on the ship. There was a clock with the home destination and a clock with the source location. And every 4 minutes difference between these clocks would be 1 degree of longitude. But there was a problem. Now, if we used sand clocks or if we used water clocks, these things would deviate by 20, 30 minutes a day. So by the first or second day of the journey, your longitude reading would be rendered useless. So this technology, really this desire to want to tell accurate time, didn't come from time itself. And there was a lot of money being offered for anyone who could solve this longitude problem. But this longitude problem came kind of out of a fluke. And in about 1602, this person here, Galileo Galilei, while staring in the Duomo di Pisa, noticed something interesting in the air, that there was this lamp and it was swinging left, right, and you see his dad was a musician. And he didn't really care about time. He cared that, wow, this thing, was keeping time really, really well. So I'm going to do a whole bunch of research on this and how it keeps track and helps me play music better. And it's interesting, this theory of this theme of music and mathematics comes up time and time again in history. For example, the Pythagoreans. But he didn't see it through. And it was in 1656 that a Dutch scientist, Christian Huygens, 1656, Dutch scientist Christian Huygens, who devised the pendulum clock. And this thing was amazing because it was accurate to the few seconds a day. No more did we have this problem between here and Craigieburn having different readings on the sundial. As long as the pendulum clocks were synced together, every now and then we would get the same time. And the cultural ramifications here were huge. You could argue that it triggered the Industrial Revolution. So potentially the first time in history, a worker's work wasn't tied to the food on their table. Rather, it was tied to their times and materials, and then they used the money to buy food. That concept of the 8-hour working day. But perhaps the biggest thing was that we now could tell time accurately across towns that were close together. Now, there were a variety of American cities, and they all had different times, and we needed a way to standardize things. And in 1883, a few people came together in St. Louis in America and said, okay, let's have time zones. And these are the 4 time zones that we see today. Once again, don't blame us software engineers. It's other stuff as well. But it still wasn't that accurate. And we went a step further. In 1928, a scientist from Bell Labs, Warren Marrison, who was experimenting with tech in quartz crystals, noticed something really interesting, that they were vibrating in a real constant manner. And from here, he devised the quartz watch. And this thing was amazing, I tell you what. Because with this thing, it was accurate to the millisecond. And from here, we get the microprocessor. And from the microprocessor, we get computers and big data and AI. And we perhaps don't know yet the cultural ramifications or the cultural progress, technological progress that we get out of this. But there was a problem. There was a tiny little problem. This quartz thing was so accurate that we realized that the Earth revolving around the sun and the Earth revolving around its axis wasn't constant at all. It just wasn't right. So that hundreds of years of research and all that stuff was rendered useless. And in 1997, the International Bureau of Weights and Measures said, the measures showed that irregularities in the rotation of the Earth made this an unsatisfactory definition of time. So you know what they did? They changed the definition of time. And this is going to be a test to me. Big breath, big breath. The second is the duration of 9,192,631,770 periods of the radiation corresponding to transition between 2 hyperfine levels of the ground state of the cesium-133 atom. Verbatim, there's no commas here. Scientists can't write. That was hard. So we changed the definition of time. And from here, we got multiple satellites, about hundreds of satellites around the Earth, keeping track of the Earth, rotating around its axis and rotating around the sun, making sure that that time is accurate across regions. And we have things that deal with leap seconds. And at this point, I really want to emphasize to you that it's not just a coding problem. It's not just us. We have inherited a lot of these things. Now, I want to show you a few coding examples that I'm hoping will give you a bit of guidance on how to deal with these things in your code bases themselves. And the first concept I want to explain to you is the difference between what we call a naive date and the difference between what we call a aware date. Now, a naive date is a representation of a date. Something like a birthday or something like a diary entry. A aware date knows. It knows where it is in point in history. It was 0, 1, for example, second from 1970. It's aware where it is. Where a naive date would be used is a diary entry or a birth date. Where a aware date will be used is something like a transaction, where reconciliation needs to be done. So I've got a naive date here, and I create a diary entry, and I've got an aware date, and I create a transaction. Now, I hear a lot of things like, it matters which data type you use. Certain data types are better for aware dates, certain better for representation dates. That's not necessarily the case. It's how you use the data types. And in this case here, my aware date, I've passed it a date, time, kind, and this tells the data type that it is in the Sydney and Melbourne time zone. Now, if I ran this, you can see that my diary entry on the 10th of the 8th, 2019 was DDD Melbourne was great. And my aware date example is Bob sent Alice $5 on the 10th of the 8th, 2019 at 14:35 at +10. So that's the first concept I want to emphasize to you. The second concept I want to emphasize is when to use UTC and when to use local, or when to use otherwise. Now I hear a lot that always use UTC. This might not be the case. There are cases where you don't want to use UTC. But in this case, we do, and I'll show you why. Now I've got a date in UTC here, and I've converted it to a local date. If I print out this date, it is the 7th of 4th, 2019 at 02:59:59. Now what I want to do is add 1 second to this date and print it. And what I should get is, let's see, I'll just run it. 0300 on the 7th of 4th, 2019. Cool, I've added a second. Now this seems all well and good. But let me do something else. Let me add second to its UTC equivalent. I'll convert it to the date time local, and then I'll print it. So I've added 1 second, convert it to our time zone here, and print it. So the original was the 7th of the 4th, 02:59:59 at +11. If I print it. And, oh, what? Is there a bug in my code? Oh, wait, no, there isn't. Is that good? No, I don't think so. Stick to my day job. So we can see it actually goes back 59 minutes, but that's because this is where daylight saving kicks in. See, +10 here, +11 there. So it's something to be wary about when we're doing calculations. In a scenario like this, UTC would be appropriate. Well, what's another example where UTC might be appropriate? Well, I've got another date here. And this is a date in Samoa. Now, if I printed this out, this is the 31st of 12, 2011, 23:59:59 -10. If I added a second to this Samoan date, and I print it, I'll get New Year's Day. Awesome. But let's do what I just did previously. Let me convert it to UTC. Converting this time to UTC. Add a second. Convert it back to Samoa time zone and print it out. So the original was the 31st of 12, 2011, 23:59:59. Print it. What? Have we just skipped a date? A bug in my code? No, there isn't. Samoa in late 2011 decided to change their time zone from -10 to +14 so that they can trade better with Australia and New Zealand. Fair enough. So it's a rule that they want to do, fair enough. But this is why also we should rely on time zones for these conversions, because someone has built in these rules for us that come in and that we might not necessarily have to build ourselves. So rely on time zones, don't necessarily rely on offsets themselves. But there are scenarios where you actually don't want to use UTC. An example of that is when we're dealing potentially with things like refunding. Now, in a scenario where we've got a monthly subscription, and that monthly subscription, say, costs $50, and it was cancelled in the middle of the month, but we want to refund that particular person for whatever amount of days they had in their monthly billing cycle. So in a case like that, where we're billing on a calendar month rather than a rolling month, we don't actually want to use UTC. We want to use our calendar month, or the month with our appropriate offset. I've got an example here where I've got a function that passes in when the subscription was cancelled, and then how much that subscription actually cost. And a lot of this stuff's done for me. So I get the first day of the month and the last day of the month. I get the total days in the month and the days billed. Then I get the prorated cost per day. My refund will then be the cost per day times the total day billed. Now if I run this, where this was cancelled on the 15th of the 2nd and $50 a month, I would get a refund of $26.79. And the reason I use February is because February is an interesting month where it changes, the number of days change. And also the number of days change every 4 years. And in scenarios like that, you don't want to be using UTC. You could probably get it right, but it'll be a lot more hard work. The final example I want to show you is things like culture. Different areas in the world have different cultures to represent dates. Some use an era of a particular emperor, some use different things. But I want to show you, even within English-speaking countries, how much change there is. So you can see in the English-speaking countries, like, yeah, United States, kind of similar to Australia. Oh wait, Australia, New Zealand, pretty similar. Oh wait, there's like a little AM is lowercase there. Just keep that in mind as well. Let's do a bit of a recap. I want to really emphasize this thing that it's not completely our fault. There is a historical and cultural context, the date time. And please don't judge developers on their commit history. It's not all us. Be cognizant of the difference between what is an aware date, that is a point in history, and a naive date that doesn't necessarily care where it is in history. Rely on time zones and not offsets. Although most of the time we're at +10 here in Melbourne, sometimes we're at +11. Do you want to look after that in your code base? Probably not. This is done for you. Think about localization and the point of localization as well. Do you want to localize, or do you want to be opinionated in your app? It's not always the case that we localize for the sake of localizing as well, but it is a good practice most of the time. Something that I didn't talk about is interoperability between APIs. There are two common standards out there. We have the Unix time, which is the number of seconds since the 1st of January 1970. And then we have the ISO standard, which is the one below. Me personally, I prefer the second one because it's human readable. Well, at least for me. I don't know if anyone can read the top one and tell me which day it is. That would be impressive though. But I prefer that second one because it is human. And rely on maintainers and thank them. And then thank them again. And if you really, really think you've thanked them enough, then thank them again. But finally, I want to finish off by saying, time, it's complicated. It's not necessarily all our fault as software engineers. And I hope that you've all had really, really good time today and have a good rest of the day. Thank you.